Hello and welcome to SimScale. In this video tutorial, we will perform a conjugate heat transfer simulation of an LED spotlight. The objective of the simulation will be to understand how natural convection helps in controlling the temperatures developed on chips inside an LED spotlight. This is because a poor LED design with high temperatures can be harmful to the lifetime of an LED package. This tutorial teaches how to set up and run a steady-state incompressible natural convection simulation using SimScale's CHTV2 solver, extract fluid volume while keeping the solid parts intact, subdomain initialization of temperature and velocity, assign both solid and fluid materials and boundary conditions, generate a conformal mesh for the solid and fluid parts using the standard algorithm in SimScale, and finally, explore SimScale's online post-processor to analyze the results. There are two links in the description. One allows you to import the project and perform the tutorial, while the other one is a documentation link where all the steps are described in detail. Let's get started. In front of you is the SimScale workbench with the Cad model of an LED spotlight. You can see the different parts present by hovering your cursor through the parts in the scene tree. You can also hide some parts to see what's inside. If you observe carefully, our LED model is symmetric in two planes. One is the XY plane and another one is the YZ plane. Taking advantage of this, it only makes sense to simulate a 90-degree model or a quarter model of this geometry and save on computational expenses. This also helps if you want to experiment with different boundary conditions or simulation setups and try different mesh densities. The 90-degree model or the quarter model is already ready for you. And here you can see the result. The parts present in this model can be seen listed in the scene tree. Our LED spotlight consists of 3 chips of 1 watt power. However, due to the symmetry cuts, one of them got cut into half, hence named as 0.5 watt, and another one got cut into a quarter, hence named as 0.25 watt. Our geometry consists also of glass at the bottom. There is also a board, there is a connector pin, a connector base as well, and there is also an internal flow region. This won't be modeled as a solid part, but rather as a fluid part later while assigning the materials. So let's quickly understand what this tutorial is about. In LEDs, there are chips that act as power sources or heat sources, and they generate high temperatures on its surfaces. Thus, the temperature of the whole LED spotlight or package also increases. And through this tutorial, we want to know if natural convection can be helpful in controlling the temperature and keep the LED cool. So let's begin with the tutorial. First of all, we need to create a fluid domain around the LED. A good rule of thumb is that the upstream or the bottom is 4 times the height of the geometry. The downstream or the top part is 6 times the height of the geometry, and the sides can be 8 times the width of the geometry. So before creating the fluid domain based on the rule of thumb, we need to first understand the minimum and maximum values of the coordinates, and these can be found listed under the geometry info. So here you can see the minimum and maximum values of the X, Y, and Z coordinates. These will be important while deciding the dimensions of the fluid domain. To create the fluid domain, go to Cad mode. This is the place where you can make changes to your model based on the available features like delete, boolean, rotate, imprint, scaling, etc. For this tutorial, we need to create a flow volume. So go to flow volume and click on external. And based on the thumb rule, our final minimum and maximum dimensions for the fluid volume should be as follows. Once the dimensions are entered, click apply. Our fluid volume is created in seconds And if you have a closer look, you can see that its two faces are exactly coplanar with the symmetry faces of our LED geometry. Now, our model has a lot of faces that are common between two solid bodies or between a solid body and a fluid body. These are called interfaces, and we need to detect them automatically. For this reason, we use imprint operation. What imprint operation does is that it detects these interfaces automatically and assigns them as contact faces. And this is important to accurately compute heat transfer loads across these faces. Performing imprint operation also helps in the generation of a conformal mesh. We'll go through that later. For now, click on imprint and hit apply. Our two important operations are done. Let's exit the CAD mode. We are back in our workbench, and you can see that we have a copy of LED Spotlight quarter geometry. This is the geometry that we just created with the flow volume and the imprint operation. Our geometry is ready for the simulation. Create simulation. This opens up an analysis type tree. Select Conjugate Heat Transfer version 2.0. This is because our analysis will involve heat transfer through conduction within the solids and from solid to fluid, and natural convection within the fluid domain. This analysis type differs from our standard conjugate heat transfer analysis in the sense that the energy equations involved are strongly coupled between all the regions, and this enables for a significantly faster conversions. So ensuring that the conjugate heat transfer v2.0 is selected, click on Create Simulation. This will open up a simulation tree, and you can see that on the left. This is where you will define the simulation setup. We need to ensure that each node in the simulation tree has a green check mark before the simulation run can begin. If you click on the analysis type, this opens up the global settings panel. Our simulation involves natural convection, hence the velocities in the domain are really small. So a laminar model is really appropriate. Also, in natural convection simulations where the temperature gradients in the air domain are so small, it's common to use the Boussinesq approximation to account for buoyancy. This can be ensured by keeping the flow as incompressible. So, at the end of the day, we are simulating a steady state, incompressible laminar flow involving heat transfer. Under contacts, you can see 64 standard interfaces. These are nothing but the interfaces that were detected due to the imprint operation that we performed in the CAD mode. So nothing needs to be done here. The next step is model. Here we need to define the gravity. Since gravity is responsible for natural convection, enter negative 9.81 against gy, which is a vertical component of gravity. You can take help of the orientation cube for reference. Our flow is expected from bottom to top. Now is the time to assign some materials. Starting with fluid materials, we only have air domains. So click on air and click apply. The default properties are enough. You can go through them one by one and change if you wish to. So we have two air domains. One is the flow region that we just created in the CAD mode. So from the scene tree, click on flow region. You can see that it gets assigned as a volume. Another one is the internal flow region that is already present within the LED spotlight. Once these two volumes are assigned, our job for the fluid materials is done. Now coming to solid materials. We have a bunch of solids that needs materials to be assigned. Starting with the core, our core is made up of aluminium. So select aluminium from this material library and click apply. Then select core. Next in the list is connector base. Our connector base is made up of brass. So select brass and select connector base from the scene tree, and the job is done. process is similar for the connector pin. However, it is made up of copper. So select copper, click apply, and select connector pin. We also have a glass present. A glass is made up of glass. The board is made up of a PVC material. So select PVC from the material library and assign it to the board. However, this time we won't use the default properties, but change them a little bit. The thermal conductivity should be 2.5, specific heat should be 1004, and density should be 1009. Click Save. Last but not the least are the chips. The chips are made up of silicon. We'll go ahead with the default properties. However, make sure that all the 3 chips are assigned this silicon material. Save. We are done with our material assignment. Now is the time to assign some initial and boundary conditions. Initialization of flow variables close to the expected solution can actually improve the convergence rate and fasten the simulation. In this tutorial, we will change the initialization for the temperature and velocity. Usual temperatures for the chips are around 100 degrees Celsius. Thus, initializing all the parts of the LED to approximately 75 degrees Celsius can actually be a good guess. So, go to Initial Conditions. Under Temperature, click on Subdomains and let the subdomain value be 75 degrees Celsius. Now we'll assign all parts of the LED to this value. A simple way of doing that is select the flow region, right click, and invert visible assignment. This will automatically assign all the 9 volumes from the LED spotlight. Similarly, we'll do a subdomain initialization for velocity as well. So go to Velocities and select Subdomains. Selecting subdomain is important because we don't want to initialize velocity to our complete domain, but rather to a particular part of the domain. Now, this particular part can be created using geometry primitives. So we want to initialize a velocity for a natural convection plume that we expect to see around the LED. A cylinder will be a best representation for a natural convection plume. Let the dimensions be as follows. You can see that we just created a cylindrical geometry around our LED. And this is because we want to initialize velocity within this cylindrical domain only and not anywhere else. Save the cylinder. And you can see that the cylinder one that we just created is already assigned. The optimal value for the initialization of velocity will vary from case to case. However, for natural convection applications, initializing the velocity to 0.05 or 0.2 provides a good convergence in most cases. In our case, a vertical component of 0.05 meters per second for the velocity should be a good guess. We only have 2 boundary conditions to assign, starting with the easiest and the most obvious one, symmetry. Carefully assign the 16 symmetric faces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Save. Now, a very important boundary condition needs to be assigned. Go to Boundary Conditions and select Natural Convection Inlet Outlet. This boundary condition is exclusive to SimScale. How this works is, for example, if I assign this face to this boundary condition, it means that this face will act as an open surface, allowing the fluid to go in and out of it freely. So this face will act as an inlet or as an outlet depending on the situation. The velocity takes form of zero gradient. All the components of the velocity tangential to this face are 0. For the temperature, it takes the form of inlet-outlet in OpenFOAM terminology, which means that the outlet values for temperatures will always be zero gradient, while at the inlet, the temperature will be regarded as fixed value, and that fixed value needs to be specified here. I hope that makes sense. So let's assign the remaining faces, which will involve the already assigned top face, bottom face, and the remaining side faces. You can also change the name of the boundary condition just to make it more representative. Save. We are done with boundary conditions. However, don't forget that there are chips that act as heat sources, and we need to assign them. This can be done under Advanced Concepts. Advanced Concepts is the place where the presence of porous media, rotating zones, power, momentum sources can be defined. In our case, we have chips. So these chips will act as power sources or heat sources. So click on the plus icon next to power sources and select absolute power source. Starting with the first chip, select the 1 watt chip and assign a power source value of 1 watt. Repeat the procedure for the 0.5 watt chip. This time, value will be 0.5. Remember that all chips have 1 watt power value. However, due to symmetry, the power got distributed. Finally, repeat the procedure for the 0.25 watt chip. Next in the simulation tree is Numerics and Simulation Control. Numerics is the place where you can define solvers, schemes, and relaxation types. Generally, we don't advise our users to make changes as these settings are fine-tuned with respect to each case, so these default settings are enough for our simulation. Under Simulation Control, one can define how to perform iterations and how to write results. For a steady-state simulation, end time means when we want our simulation to end. So let that be 750. A delta t or time step of 1 second means that we'll in total perform 750 iterations. Write control defines how do you want to write your results. A write interval of 750 means that we don't want to write down intermediate results, but only the final one. This saves computational expenses. Maximum runtime defines how long you want the simulation to run in real time. If you don't want your simulation to stop in between, set up a good maximum runtime. a 30,000 seconds of maximum runtime should be more than enough. It will be of interest to monitor changes in variables involved in our simulation while the simulation is running. For example, the temperature on the surfaces of the chips. This will give us an idea whether the simulation is running in the right direction or whether it is stable. Thus, we'll assign some result control items to capture the average temperature on the areas of these chips. The monitoring of results can be done under result control. Setting up result control items is a crucial step in a simulation. They help us to assess convergence. We are interested in the temperature developed on the surfaces of the chips. So select surface data and go to area averages. So the area average result control item will give us the average values on the surface areas of these chips. First of all, set the right interval to 5. This means every 5th iteration, the results will be written down. Now, we need to select the surfaces of the chips that lie just below the board. So hide the board and select the face of the 1 watt chip. Save. Repeat the procedure twice for the other 2 chips. Finally, we'll set up the mesh settings. For the meshing operation, the standard algorithm of SimScale will be used. This is a good general choice and is quite automated. It delivers good results for most geometries. The default settings will be enough. Let's go through them. Under sizing, you define how do you want to size your mesh cells. A fineness of 5 should be enough. We also want some boundary layers to be generated. Number of layers should be 3 with an overall relative thickness of 0.4. The growth rate between each boundary layer cell will be based on its adjacent cell with a growth rate of 1.5. The meshing will be physics based, which means that the information from the materials, boundary conditions, the additional advanced concept terms that we have set will be taken into account while the mesh is being generated. Hex element core means the interior of our domain will be covered with hexahedral elements, and the transition to the triangulated surface mesh will be covered using tetrahedral and pyramidal elements. Keep number of processors to automatic, and under advanced settings, just change the cap refinement factor to 3. This means that a minimum of 3 cells are ensured across thin elements or parts. Don't generate the mesh yet, just save. The mesh that will be generated will be of conformal kind. That will be explained later. If you wish to, you can also add some refinements to the mesh. For example, a region refinement can be added to a cylindrical volume around the LED, just as we did for our velocity subdomain initialization. And you can ensure that the maximum edge length is small enough so that the mesh around the LED is more refined. This can be done to capture the natural convection plume better. However, this won't be needed. We are ready to begin our simulation run. So click on the plus icon next to simulation runs. This will open up a dialog box with an estimation of resources that will be consumed. Rename the run if you wish to, or keep it as default. Start the simulation. Our mesh will be computed first, followed by the simulation. The status of the job can be followed under job status below the simulation tree. The meshing takes around 10 to 15 minutes to finish, and the simulation begins right after that. Few minutes into the simulation, and a solver log is provided under the run. Here, the exact output of the actual computing algorithm is written down. The best part about using SimScale is that while the simulation results are being calculated, you can already have a look at the intermediate results, either under Convergence Plots or area averages that we have set up, or under solution fields, which takes you to the post processor. The simulation takes about an hour to finish. Let's have a quick look at the mesh. The details of the mesh can be found under event log. Here, you can find the number of nodes, edges, faces, number of tetrahedral, hexahedral elements, along with prisms and pyramids. There is an important statement at the bottom. This is a conformal multi-region mesh. Now, what is a multi-region conformal mesh? Multi-region belongs to different regions that we have, for example, solid and fluid regions. And a conformal mesh means a congruent mesh across an interface. And what does that mean? Let's say we look at this interface, which exists between this part and this part. So, in a conformal mesh, the cells adjacent to this interface will share the vertices, edges, and the face. This is called conformal mesh. And this is important when we want to map the values at the cell center to the face and from the face to the cell center of another cell. This trend can be followed across all the domain. Meshing log and mesh quality features are always present, and they come handy when a user wants to explore the mesh in detail. Don't forget to check them out. Now, let's have a quick look at the result control items that we had set. So under the run, go to area averages, and here you can find the 3 area average values or result control items that we had set. For the first chip, this plot shows how the chip temperature is evolving as the algorithm performs iterations. In a converged simulation, the temperatures will stabilize and no longer change between iterations. In this case, you can see that for just about 400 iterations, our values stabilize. This trend can be seen followed by all the chips. So you can see that at the end of 750 iterations, the value of the chip surface for chip number 3 is approximately 369 kelvins. We can also have a look at the residuals from the convergence plots. Residuals are nothing but the measure of an error in the solution. And we of course want it to be as small as possible, because this is inversely proportional to the accuracy of the solution. So the smaller the residual, the higher the accuracy. The residual is evaluated by substituting the current solution that we obtain from an iteration into the equations, and then you just take a magnitude of the difference between the left and right hand sides of the equation. And the residuals are also normalized so that they are independent of the scale of the problem being analyzed. For this case, we can see that our residuals are pretty much low and they also stabilize. Now is the time to jump to the post processor. Click on Solution Fields. This will take you to the post processor. Make sure that you are at the end of your iterations and there are no additional filters. For this simulation, we are most concerned with the temperature. So make sure that under parts color, your coloring is temperature based. Zooming into the geometry, we can see that the chips have the highest temperature, and the LED as a whole is pretty much cool. You can change the temperature units to degrees Celsius, and if you right click on the legend and use the continuous scale, then you can see a smooth variation between the temperatures. Inspect point feature comes handy if you want to have a look at certain points in the model and check what's the temperature at that particular point. The different parts present in the geometry are listed here. And if you want to take a look at the temperature inside these parts, then just hide them. For example, if we hide the connector base, then we can have a look at temperature at a particular point inside the connector base. The coloring can also be set based on the velocity magnitudes. However, we need to toggle on the flow region so that we can see the development of the natural plume around the LED. You can see that the maximum velocity developed is around 0.5 seconds. Now let's visualize this natural convection plume using streamlines. So set the coloring back to temperature, go to add filters, and let's add some particle traces. Make sure that the seeds horizontally and vertically are 10, and the spacing between them is as follows. Let the coloring be based on temperature, and the rest of the settings should be as it is. Now we need to pick a position to set up these streamlines. So click on pick position. If your flow region hides, toggle it on back and find a suitable place to place your seeds. Now if you hide your flow region, you can see the development of the natural convection plume. We'll add some more particle traces. So toggle on the flow region, add a new filter, particle trace. The settings will be same as before. However, the placement will be different. Pick position, randomly placing the seeds on one of the sides of the flow region tells us that as the hot air around the LED rises, it draws the cold air from the bottom as well as the sides, leading to natural convection. Finally, we'll set up an animation. Make sure that the animation type is set as per particle trace, and you can adjust the steps and animation speed accordingly. Hit play. This brings us to the end of today's session. I hope you really enjoyed it and learned something valuable. Let me know your thoughts in the comment section. See you next time.